Hi there and welcome back to the Good Tutor Premier Prep SAT course, and in this video we'll continue our look at the Heart of Algebra subsection of the SAT math sections, and specifically we'll be taking a look at systems of linear equations, which will be very similar to the linear equations we've already been viewing, but now we'll have more than one of them at a time. Right, so for a quick introduction of systems of linear equations, or really systems of equations in general, we want to define what these systems are, and really these systems of equations are just more than one equation, and in our case, two. And the solution or solutions to these equations, or these systems of equations, will be the points where these lines intersect. Or where they touch. It's the same thing as intersect. Now, there are two ways, though, to solve a system of linear equations, the first of which is called substitution, and we'll view in this first problem. So we're given the two equations, if 4x plus 2z equals 16 and x plus z equals 6, then what is the value of z? So we're actually not looking for the solution, in this case the full solution, we're just looking for the value of one individual variable, in this case z. All right, so substitution, as the name implies, was eventually going to have us substitute or replace one thing for another. So if we go ahead and write out our system of equations, 4x plus 2z equals 16, and x plus z equals 6, well then really the easiest way that we're going to be able to solve this one is to isolate either x or z in that bottom equation, because we won't really have to do much to isolate either one of them. So let's go ahead and solve for, or isolate x in this case. So if we take z away from both sides by subtraction, because it's currently being added, we'll be left with x is equal to really negative z plus 6, or you could put 6 minus z. They're both the same thing. So now that we have a value for an isolated x, we can go ahead and plug into our original equation. And instead of wherever we'll put in x, we will now put in negative z plus 6. So let's take it back to that first equation. 4 times, instead of x, it'll be negative z plus 6 plus 2z is equal to 16. Now, the next step will be distributing that 4 to everything inside those parentheses, which will leave us with negative 4z plus 24 plus 2z is equal to 16. Before we go any further, we'll want to combine like terms. And in this case, those like terms will be negative 4z and 2z. So a negative 4 and a positive 2 combine to make a negative 2. So negative 2z plus 24 is equal to 16. And now it's just a matter of isolating z. We'll first want to rid the left side of that 24, and it's currently being added, so we'll do the opposite operation to both sides and subtract 24, leaving us with 2z is equal to negative 8, or negative 2z is equal to negative 8, I should say. And now, since negative 2 and z are being multiplied, we'll divide the 2. Dividing both sides by negative 2 will result in z is equal to 4. Which is actually all this problem is asking for, as we said in the beginning. All right, the other method for solving systems of linear equations is known as combination, in which we'll find a leading number or numbers that will help us cancel out one of the terms or one of the variables in the two equations that are given. So in this case, if we want to look at this problem, we have if the point xz is the solution or is a solution to the system, what is the value of z? So again, we're looking for the value of z in this one and not the full solution. All right, so if we write out our system of equations, 4x minus 7z is equal to 27, and 2x plus 4z is equal to negative 9. I think the easiest term in this case to cancel out is going to be that x term, because 4 and 2 relate to each other pretty obviously. So we have to ask ourselves now, what can we multiply that entire bottom equation by to make it so that it will cancel when combined with the top one? Well, you may think multiply by 2 and it will be 4. but then that would actually combine to be 4x plus 4x and make 8x. So we need the opposite sign. So if you're thinking -2, you'd be correct. Now we'll distribute that -2 to everything in those bottom parentheses, but we're going to leave the top equation exactly how it is. So let's see what this combines to. So now we'll have -4x minus 8z is equal to -2 times -9 is a positive 18. So now let's rewrite the two equations we have. 4x minus 7z is equal to 27, mixed with our new equation, which is -4x minus 8z is equal to 18. All right, so as planned, our x's cancel out, and we are left with -15z. And this is just combination by addition, essentially, now, between the two new equations, or the one new equation and the original. And then 27 combined with 18 would be a positive 45. Now, because -15 and z are being multiplied, we'll divide both sides by -15, which will give the answer that z is equal to -3. All right, and the last thing we'll take a look at is when we look at the graphs of systems of linear equations, there can be no solution to a system, there can be one solution, or there can be infinitely many solutions. And I'm going to show you how, both graphically and with the equations, we can reach each one of those. So no solution will actually mean that two lines are parallel. So if we take a look at something like y equals 3x plus 2 and y equals 3x minus 3, and we see that those two equations have the same slope, which if you watched our last video would know that those two lines are parallel. And parallel lines have the same slope and actually have no solution because they will never touch because they move exactly the same. They move at the same rate with that same slope. So if we graph these two, we have a y-intercept of that first equation would be positive 2 right there. And then that rise over run of 1, 2, 3 over 1. All right, there's 1. And the other now is 3x minus 3. So 1, 2, 3 negative is the y-intercept. So for this one, you'll see these graphs move exactly the same, and they will to infinity. All right, one solution, or equations with one solution, we just saw actually examples above where we would get one value for x and y, or in those cases x and z, where, and I'll just quickly sketch one like these, where two lines will hit each other at a single point, and that will be the solution. So in this case, the one I just sketched here, the area of intersection there that I kind of highlighted in red would be our solution, the exact point of that intersection. All right, and then infinitely many solutions are actually two equations that end up being exactly the same. And that would make sense that if they're the exact same line, they would end up having an infinite number of solutions. So for example, if we had 2x plus z is equal to 10, and 4x plus 2z is equal to 20, well, if we just divided that entire second equation by 2, we would see that it's actually exactly the same as the top equation, which would be the exact same line. And if we were to put that into y equals mx plus b form, it would still be the same line. So if we were to just sketch it, it would just really be one line, right? Because it's two ways of expressing the exact same line. All right, that's it for this video. Up next, we'll have solving linear inequalities.